Good morning, good evening, everyone. Today, I will be talking about the story of slope fields and isocyclines. So, imagine you're a sailor crossing the Atlantic Ocean in the 1970s. There's no GPS, no satellite, no weather forecast. All you have is a map and a compass and just the wind. As you sail, you cannot see the destination. In fact, most of the time, you don't even know exactly where you are. But at every moment, you know one thing: the direction of the wind is guiding and pushing your ship. So if you continue to follow these directions, like little by little, slowly by slowly, like there's going to be a path, like a path will emerge. So now imagine placing thousands of little tiny arrows across the ocean, each showing the direction of wind that would push you to that location. Looking at all those arrows combined together from like the big picture overview, you could predict where your ship is supposed to travel and will travel, even without seeing the exact route beforehand. And this is surprisingly similar to the idea behind slope fields. During the 17th and 18th century, scientists were trying to understand some of the biggest questions in the world. How do planets move around the sun? How do diseases spread through populations? How does a population grow over time? How does heat flow through an object? To answer these questions, mathematicians such as Isaac Newton and Gottfried Wilhelm Leibniz developed calculus, one of the most powerful tools ever created. So using these calculus, these mathematicians and scientists could write equations that describe how things change. But soon they realized there was a big problem, because many of these differentiable equations were incredibly difficult, or sometimes even impossible to solve exactly. For example, like imagine being given a treasure map where someone tells you, I can't show you the treasure, but I can tell you which direction to walk at every point on the island. At first glance, this may sound useless, because like that's not showing me where's the treasure. But mathematicians realized that this was pretty good, because if you know the direction at every point, you can reconstruct the whole entire path. And this idea became the base and the pillar for slope fields. So instead of finding the solution directly, so they were able to visualize how the solution behaved and like that path to the treasure. So now I'm going to talk a bit about the birth of isocyclines. So as mathematicians began like drawing these slope fields, they like saw another pattern. They noticed how like certain points on the graph shared the exact same slope. For example, one curve might only contain slopes equal to 1 or 2, right? Another might only contain slope 3, or another might only contain slopes that equal to 0. Rather than calculating every tiny line segment individually, they found a much more efficient way. They could identify these special curves first, and these curves became known as isocline. And a bit about the history of this. So the names come from Greek. Iso meaning equal, and cline meaning inclination or slope. So literally isocline literally means a line of equal slope. So these lines acted like contour lines on a topographic map, helping mathematicians understand the structure hidden inside a slope field. Okay, back to the real world. So today, slope fields and isoclines matter so much more than like a classroom subject, because like for example, scientists like use these similar models to model like disease outbreaks. Like even engineers use them to study like changing systems. And I recently learned that economists also use differential equations to predict growth and decline in my macroeconomics class. So even modern weather forecasting relies on understanding how like conditions evolve over time. So all these applications begin with the simple question: if we know how something is changing at every moment, can we predict where it will go? Slope fields and isocline were developed to answer exactly that question. And before we solve any questions, they allow us to see the behavior of a system. So before we learn how to draw them, let's first understand exactly what a slope field is and isocline are. So I will give you guys a 10-second break. Just kidding, audience. There'll be no break. So, let's start with slope fields. So suppose I gave you a differential equation, dy dx equals x plus y. At first glance, this equation may not tell us much. However, what it does tell us is that the slope of a solution at every point on the graph. So for example, let's look at the point 0, 0, or the origin. So if we substitute the value, we will get dy over dx equals 0 plus 0 equals 0. So this means that the slope at 0, 0 is 0. So we would draw a small horizontal line segment there. So now look at the point 1, 1. So same thing, dy over dx equals 1 plus 1. Sorry, that's supposed to be 1 equals to 2. So here, the slope would be 2. So that means instead of like just being 1, the slope will be like sloping upwards more because higher number is steeper slope. So it'll be pretty steep. So last example, let's look at the point -1, 0. So we would plug it in, dy dx equals -1 plus 0 equals -1. So there, the slope will be negative. So that means it will be tilted down slightly. So like this, slope of -1. So at that point, the slope will be slightly tilted down. So if we calculate these slopes at hundreds of points and draw tiny segments everywhere, we'll create what is called slope field. But hundreds is a bit of a stretch because that is a lot of points. A slope field is essentially a map of directions. Every little segment tells us which way a solution curve should move at that location. Instead of solving the differential equation exactly, sometimes we can understand the behavior of these equations by just looking at the maps of slope fields that we graphed. Let's move on to isoclines. As mathematicians drew slope fields, they noticed that some points shared the same slope. So let's use the same equation from last time, dy over dx equals x plus y. Suppose we want to find all the points where the slope equals 0. So that means we would set dy dx equals 0 and make x plus y equal to 0. And that gives us y, making y the subject, y equals -x. The line is an isocline because every point on it has the exact same value of 0. So for example, we can use points 1, -1, 2, -2, -3, 3. All have slopes equals to 0, m equals to 0. So now, for example, let's find where the slope equals to 1. So we can do the same thing, making x plus y equal to 1. So in this case, y would equal to 1 minus x. So for example, points out has slope equals to 1 would be 0 and 1, because that would satisfy the equation 1, 0, 2, -1. All have slopes equal to 1. Similarly, if we want all the points equal to 2, we can do the exact same process. Brings up something super interesting that I want to tell you guys. So since each isocline is a line connecting points with the same slope, while the slope field contains all the possible slopes at all points, a good way to think about this is that a slope field shows the entire weather map, and an isocline is like drawing a contour line that highlights the region with the same weather conditions, like light, so a region where it's light, heavy, or rain. Heavy being like steeper slope, like a region where there's steeper slope, and light where it's like less steeper slope. Okay, I'm not sure if you got that, but I thought that was pretty cool. So together, slope fields and isocline can help us understand how a solution behave without even solving the differential equations. So now we're going to look at a visual example of the slope field. So at first glance, this graph may look like a collection of random line segments. However, at each of these little line segments, it represents the slope of a solution at that specific point. So for example, at 1, 0 over here, and 1, 2, it's a different one. So notice that in some region, the line segments tilt upwards, like here, and some tilts downward. this indicates positive and negative slopes. So as we move across the graph, the direction of the segments gradually changes, as you can see. And this tells us that slope depends on where we are on the coordinate plane. So the key idea is that these segments act like directions in a map. So if we place a pencil at any point and then trace a curve in the segment, it will begin to reveal a solution of the differential equation that we're looking for. So this is why the slope field is so powerful, because we don't have to use any algebra and we can just visualize it with drawing. Now for a visual example of the isocline. In this image, the red lines are the isoclines. An isocline connects the points that all have the same slope value. So in this case, these red lines have the same slope value, because as you can see right here, the slope is facing the same direction. So for example, the line labeled k equals 0 contains points where the slope is equal to 0. So the line segments along that curve are horizontal. So notice that every segment touching the same red line has the same orientation, just that because they share the same slope. So a good way to think about isoclines is to compare them to contour lines on a topographic map. Contour lines connects points with the same elevation, while isoclines connects points with the same slope. So while slope field shows the direction of the change anywhere, isoclines, it helps us organize where these regions are showing the same direction. Guys, I hope you guys enjoyed the video. And lastly, so for practice problems, you guys can check out 599, 613, 642, or 657. And if you guys enjoyed the content and want to see the solutions of how to do these 4 problems, please like and subscribe and drop a comment below. Thank you and have a nice day.